And welcome to the playlist in which I'm breaking down all of the ACSL contests and any content that you might see on your test. So today I'm going to be going over all of the multiple choice that you could receive on your ACSL Contest 4. This is part of the ACSL Road to Gold playlist in where I'm going over the finals and multiple choice content for the preliminary rounds. So today is Contest 4. So the first topic covered on Contest 4 is graph theory. So some necessary vocabulary prior to beginning the problems is what a undirected, directed, and complete graph is. So first of all, a graph is a collection of edges or nodes and vertices, and an edge is this little line here that will link two nodes or two vertices together. So an undirected graph is a graph where each edge connects two vertices symmetrically. So an undirected graph has no direction. You can see that this graph right here is an undirected graph. A directed graph is one where the edge actually points from one vertex to another. So here you'll see that there's arrows going from one node to a different node. And in a complete graph, every pair of distinct vertices is connected by an edge, meaning that all of the vertices have a path to each other, essentially. If you're a combinatorics person, then you know that you can figure out mathematically how many edges there is in relation to how many nodes there are on the graph, like so. So this is a completed graph because all the nodes are connected to all the other nodes. So a path is a sequence of vertices where each consecutive pair is linked by an edge. So for example, if we're going from A to D, we can go AB and then BD. And then that's our path. We could also go to AC and then CD. So there's multiple ways, but both of those would be examples of paths. And a cycle is a closed path that starts and ends at the same vertex. So for example, if we're going from A and we would go back to A to create a cycle. So we would do AC, CD, DA, and then we keep going. So here, this is an example of a path from A to C. It's just AC. And then a cycle would be, okay, so this one says AB, BD, DA. So you can see how this creates a cycle. Next is trees and forests. So trees is a connected graph with no cycles, so one path exists between any two vertices. A tree with n vertices will have n-1 edges, so this is typically what a tree is going to look like, and a forest is a collection of trees, but these trees may not be connected to each other. So what you're typically going to have to do for these problems is construct an adjacency matrix. So an adjacency matrix is what you use to determine how many paths there are of a certain length from one node to the next. So for instance, if there are 4 nodes in the graph, you'll need a 4x4 adjacency matrix. So this is my adjacency matrix for this graph right here. So what this means is there a path from A to A of length 1? Because there is none, I'm putting a 0. Same goes for B. There's no path from B going to B that is of length 1. For C, however, we have this little loop. So this loop in ACSL could actually mean an infinite number of steps. So C technically has an infinite number of paths of different lengths that could get C to C. But C, we do one loop, so that's length 1, and we're back at C. So I'm putting a 1 here to represent that that's true. From D to D, we don't have a little loop, so we're going to put 0. Now, the same goes for the others. So from A to B, there is a path. From A to C, there's a path. From A to D, there's a path. From B to C, though, we don't see a path, which is of length 1. So that's why I put a 0 here. And the reason that these are different is in the case that you're working with a directed graph, then you would need to actually figure this out because we're using an undirected graph, B to C is the same thing as C to B, but so you'll notice that the graph is symmetrical. However, in the case that we're using a directed graph, you would need to clarify A to A, B to A, and then this would be like A to B. So essentially you need to, or B to A, sorry, B to A and then A to B. You would essentially need to make sure that you understand which one is the first node in the sequence, which to which, for a directed graph, because it's not going to be symmetrical in that case. And the reason this is useful is because if we square the matrix, the value in the cell ij indicates the number of paths of length 2 from vertex I to vertex j. Or if we multiply the matrix by some power of n, then the value in a certain square is going to be the number of paths of length n from the vertex, in this case A to D. So this is what they're typically going to ask you in ACSL. They will ask how many paths of length 4 are there in this matrix from B to C. So you would have to put this matrix to the power 4 and then see what value there is in there. The next topic that is on the ACSL contest is digital electronics. So essentially what you need to know for this is how to convert between diagrams and equations. And then after you convert to an equation, it should be a smooth sailing ship, because I have some past videos going over how to solve Boolean algebra expressions or digital expressions. Okay, so here I pasted in a diagram I found on ACSL Wiki, which essentially explains what each picture could mean. So I'm using this as an example here. In the problem example, we have A NAND B, so I did NAND AB, and then that value is going into OR C. So make sure that you're using your parentheses so you can actually tell which value is going in where and what operations you're solving first, because sometimes you can't always tell. And now to solve this expression, you would simply create a truth table. So this expression is only false under one condition, and you would do this just by manually plugging in the values into the written equation that you got, so in this case NAND A, B, or C, and seeing which ones evaluate to true or false. So that's kind of how you would solve these. Frequently, ACSL will ask you how many expressions evaluate to false in this diagram, or list the expressions that evaluate to false in this diagram, so that's typically what you would be asked. The last piece of content that's covered on ACSL Contest 4 is assembly language. So assembly language has 3 columns: the label, opcode, and lock. So the label is going to be like a variable of some sorts. You don't always use one, but sometimes. Opcodes is the actual function, what you're doing to it, and lock is the memory reference, so what's going on in the memory. So the accumulator in assembly code is essentially the address in memory that keeps on getting data or new bits added to it. So usually ACSL will ask you the contents of the accumulator. Sometimes it'll ask you the contents of a variable. So I uploaded from the ACSL wiki this little table which essentially explains what each kind of operational code would do to the variable. And I have an example problem here in where, see, we're storing 8, -2, and 3, and these variables load B, that puts the contents of B into the accumulator, so the accumulator is -2. Then you're multiplying it by C, so no new memory address is specified here, which means that we're just multiplying the accumulator by C. Adding A, dividing by B, and subtracting A, so essentially we're doing all of that and we get to -9. Now we're storing that value in a variable called temp, or a memory location called temp. So then it's saying, this question asked what the value of temp was at the end, so temp would be -9 at the end of following through all of these operations. So that's all I have for today of ACSL Contest 4. I hope that these videos and problems were useful, and if you would like a finals video, then let me know. But bye for now.